Hello everyone, welcome back. Let us start. We have been talking about the effect of transmission on stiffness. We started on this topic in the last lecture. So, what we understand, we try to explain from the very simple example. Just take one link or a lever and then try to place the spring at different location and see what is the effect. And what we understand then, if we simply move the spring from the end to the mid section, so what we realize there is a large effect. So, initially if it is co-located, you just feel the stiffness of the spring, but moment you move to some other location, the leverage or what we call it transmission, that will come into picture. And what we realize that the effect on the stiffness is very high. So, actually it is not just linear, but it reduces the square terms. So, that we explained already. And so, if we define transmission ratio as like V out by V in, so where like V out is the point of interest where we are applying the actuation or the force, and in is the placement of the spring. And in this case, if we compare and we generalize it, what we realize that the equivalent stiffness is k over I square. So, now we can see that there is a huge impact, and just moving the spring location, or the if we are like talk about general machine design, and when we are talking about the load path, now we realize that the members placed or coming in the load path and the stiffness of each and every member, how is important. Even the placement, the location of that part will affect the overall stiffness by to a very large extent. So, we will try to see with the more example, and I think when we apply these things in the design or any transmission design, we should take care of these things. So, one very good application is also the belt transmission or the cable transmission. So, what happens if we put any belt or cable and pass over different size of pulleys. So, yes, we are just talk about belt stiffness, but it also applies to any kind of cables or wires. So, the belt stiffness, suppose this is what we are talking about, and so this is the area of cross section, and we apply the force F, and because of this force, what is the extension? So, there will be some displacement delta, and that is how we define belt stiffness. So, it is getting a stretch, we apply tensile force. So, belt usually they work only in tension. So, that we already know, and if K is the belt stiffness and it is going over a pulley, so what happens? So, what we might be interested in knowing the rotational stiffness, because these belt driven systems, they are attached to different elements and there are many shafts attached, right. So, in and out shafts can be attached, and so we can think of so in and out two shafts, there is maybe input and output shaft connected, and okay, is applying some torque T. So, what happens if we just try to translate and try to find the equivalent stiffness and the shaft, or the talk about the rotational stiffness, how is it related? So, what we can do is either we can just we can say we fix it. So, in some way we call fix it, or we can say simply fix this part, cut it and fix it, and try to apply a load. What happens here? There will be F acting on the belt. So, the way we define rotational stiffness is a kappa. Yeah, means maybe notation wise we might have some issues. So, either we call it kappa, or equivalently we can also write K and subscript put rotation to avoid any kind of confusion. But this is the torque applied, and what is the deflection theta. And when we try to relate these two, what we understand from here, the equilibrium condition if we put, or if we try to make the free body diagram, what we realize that T is nothing but F times R, the radius of the pulley. What about delta and theta? So, what happens if this end is fixed and we try to apply the torsional load, apply the torque, because the stiffness K, there will be an extension which is delta here, and because of that delta, what we also realize that there will be rotation theta, it will be that elastic deformation will be there, and because of that delta there will be theta rotation also. So, that is also related, and what we can say delta is theta times R. And if we try to put them together, what we can easily write, T is your F R and theta is now delta by R. And if we just say kappa here, the rotational stiffness, what we realize that is F by delta, and this R will also go up. So, we have R square. So, basically what we are getting is belt stiffness times R square. So, when we rearrange, what we realize that this rotational stiffness is equal to K times that is the belt stiffness into R square. So, it is the square of the radius. So, what we realize that if the radius is large, there is a huge impact on the rotational stiffness. So, if we are designing things and designing any kind of transmission using belts or cables, wires, any kind of flexible transmission we are designing, and if you are aware of this thing, we can choose the diameter of the pulley accordingly. And or suppose if we have a design, and with respect to the dynamics or vibrational characteristics, if we are facing some problem, and suppose if we want to have a resonances or omega naught or omega 0. At higher frequencies, we know where we can make changes, and it's a square term. So, you can see here that if you the same belt, if you are putting on a larger pulley, we have very large rotational stiffness. So, if we simply compare the two designs 1 and 2, where a small r is smaller than capital R, what we realize that the rotational stiffness of the larger pulleys is way higher, is capital R by R square. So, this will make a huge difference. So, I think one should be aware of this and then use it accordingly in your designs. So, larger pulley diameter increases rotational stiffness, and be aware that is a square terms. So, this is very important, it is not linear. Another very good example, and we may encounter in our designs, or there are many designs built on these concepts. So, what happens if any member is not longitudinally placed, but at a slant. So, for instance, it is a K here, so it is a spring here. But what you can also assume that this is just a bar. Having a stiffness K, longitudinal stiffness K, if that is there, and then if force F is applied vertically, of course, in this case we have idealized it and supported against the wall. So, what happens? What happens to the stiffness? What is the stiffness experienced here by the actuator or wherever we are applying the force? So, the direction is given, and suppose it is slanted at this angle alpha. What is the equivalent stiffness? So, again, after working through, we may realize that it is a square terms, and then it is a cos square alpha. So, K is the stiffness of the link, but since it is not aligned and there is a deviation, there is a slant alpha, what we realize that is a cos square alpha. So, what we realize here also that if this angle is little high, so this deviation will be very big. So, one should be aware of that and design it accordingly. So, we will go through how we will arrive at it. So, first what we can do is we can do the force analysis. So, what we need to understand is what is the force coming on this spring here, what is the force coming here when there is a F applied and it is supported against the wall. So, there might be a normal force also. So, I think one has to be aware of this. So, how is coming, I think one need to understand that, and yeah, if anybody has any doubts, you can always write to me and we can discuss that, but I will try to explain here. So, first we try to calculate forces. So, there are some methods, and graphical methods sometimes very easy and can be easily understood. So, suppose this is F force acting. Since this member, this link, call it a link or a spring, there are two revolute joints. So, I think what we know that it's a binary link, and any member which is only connected at the ends with the revolute joints, the forces under equilibrium. If there are no other forces, the forces will be always along the longitudinal axis. So from there we know that this is the direction. So it will be along that line. So this is what we have. Call it a spring, for instance, in this case. So the direction, even if we are not sure about the direction, at least we know how, or the arrow I would say, whether it's pointing upward or downwards, but direction we know. Similarly, in this case, what happens is supported against the wall, so there will be reaction force also, and since there is no friction, not friction involved, so there will be only normal reaction. So again, maybe we are not aware of the arrows, whether it was going left or right, but yes, we know that it will be in this direction. So it's a triad, and many of you might be knowing how to solve it, but I'll just try to animate and try to show. So what we can do is, since we know the directions and it's under equilibrium, so if we add all of them, so the forces acting here, what we realize that it will be like this. So it's very intuitive in this case, but many times that may not be the case, and in that case it's very important to just draw it. And if we draw it to the scale, what we realize that if it's to the scale, so suppose we know f, so taking some scale, and if we do, so the magnitude direction is known, and since it has to be close, so and the direction is known, so Fs has to be like this, and n has to be, then only it will come to the same location. The order can be different, but we can use a parallelogram theorem, and you can change the order also. So we can place n here and then can also do this. So we can also start like this. So but we'll get the same direction and magnitude. So there should not be any problem. Yeah. So parallel. So once we know, yes, graphically we can do that. We can just measure and then again multiply with the scale what we have used, and we also know the magnitude. Otherwise also, since we know the triads, and so this is the applied force F here. Now this is the spring force. So this is the force talking about, and if we do little mathematics here, what we realize that this is nothing but F times F by cos alpha, or other way also what we can say is F by Fs is cos alpha. Using normal trigonometry, we can write that, and then we can also write Fs in terms of F. So if you apply force F, what is the force experienced by the spring? If we know K here, what we also know that if K is the stiffness and Fs is the load coming on that, then the delta, the deformation in the spring will be Fs over K. So first we try to find forces, and then we can also find the displacement or deformation, and then we can again translate into the displacement along the force direction. So, for that again we can deliberate on that, and for instance, if this is the length, so this is the position of the link of this spring, and this is the angle alpha, slant angle. So, when force is applied, this has moved here. So, this is the displacement because of the force F, but we also realize that what is the deformation in this spring. So, we drop a perpendicular, and what we realize that this is delta S, and this you can say delta prime, and again is for very small deformation. So, we can easily relate is the trigonometry. So, delta S and delta prime, and what we again we can write the trigonometry, and what we realize that the displacement in the vertical direction or in the force direction is function of delta S, which is delta S by cos alpha. So, once we know the relationship between the two, we can easily find out what is the effect on the stiffness because of this slant angle. Another approach is also talking about the transmission ratio. So, here we can also talk about that, and what we realize that transmission ratio is defined versus. So, what is the output here? So, where we are interested in. So, we are applying force in the vertical direction. So, what is the deformation in that direction? That is delta prime or delta dash, and N is where the spring is located and along that direction. So, in the longitudinal direction, the deformation in the spring in delta S, and we just derive that if we try to find the relationship is a 1 over cos alpha. And what we derived earlier is a k times I square, and if we just use that, what we find I is 1 by cos alpha square, and therefore, what we can find is k times cos square alpha, because cos alpha will go in the numerator. So, from here also we can find, but we can also use the two relationships. So, what we derived is the force relationship. So, applied force versus force coming on the spring or experienced by the spring, we derived it already. We also derived the relationship between the displacements, deformations. So, what is the deformation in the spring, and equivalently what will be the deformation in the vertical direction or in the direction of the force that we derived. We also know that this K, the spring stiffness, is the force experienced by the spring over deformation in the spring, and when we work out what we realize the stiffness in the vertical direction, or in this case in the direction of the force applied, k prime, which is equal to, or k dash, which is equal to force versus delta prime delta dash, and this is what we get. So, k times cos square alpha, and again this square we should remember and be aware of. It is not linear, but it is varying with respect to cos square alpha in this case, and cos alpha already is a reduced value, and even a small change in alpha that can make a huge impact. So, one should be aware of that while designing, and one should be also able to know that why, if we are doing some characterization and running some experiments and the stiffness values are not what we are getting, it might be because of there is a small deviation. So, one should be able to put it and calculate it and should be able to get the right numbers. So, it is very important. Yes, here we tried the approach and we try to use force equilibrium conditions and the geometry. As a mechanical engineer, many times people may find it very intuitive way to do, because you know what are the forces, what are the directions. But at the same time, yes, we have to be aware of the directions and we have to write it correctly. Another approach, and when things get complicated and too many connections, we use energy methods, and many times it is very convenient and very simple principle. Half k x square, that is the potential energy stored, and work done is accordingly half f delta. Or if you are talking in terms of equivalent stiffnesses, that will be half k prime delta prime square. So, moment we know one relationship. So, if we are able to derive the relationship between the in and output and we are able to find it, no need to calculate everything, but we can straight away put it there and we can find what is the effect on the stiffness. From there also, so if we write k x square, here we have x square term coming, which is a deformation thing. So, it means, and that is why when we are talking about I transmission ratio, here we are talking about the ratio of the two deformations. So, V out by V in, or deformation out by deformation in, and from here also we can relate that k prime is nothing but k by I square. So, it is easy to correlate, but energy method is also a very powerful tool, and we can always cross check our calculations with that. So, another question we may impose, or what happens if I put another spring k the normal direction, what happens to that? So, I think this would be very good exercise, having same k and just try to find. So, there will be some very interesting results. So, when the two springs, same springs, what happens if they are connected orthogonally, how the stiffness changes. So, it is a very good exercise, and anybody interested may like to work on this problem. Yeah, we will be talking about these things later when we take some examples and talk about the trusses. So, we will see in the coming lectures. There are many cases where the links are connected in different ways, and not just like it's in what we have understood till now, either they are parallel or they are inline connecting end to end. What happens if it's not connected in that fashion? So, like this kind of arrangement shown. So, it's just a truss, and what we are saying that is in series. So, if you are applying a force F here, what is the K prime? What is the stiffness? Because of the stiffness of these two links. So, if the two links have the longitudinal stiffness given by KAB and KBC, which is basically EA by L. What is the effective stiffness in the force direction, and whether it will be good enough. So, of course, we are using the axial stiffness. What we have to also ensure that if this is the design, whether this is true, whether we have only axial forces coming on the links. So, and in many civil constructions, bridge designs, tower designs, and even machine frame design, I think it would be a very useful tool. So, the trusses can be designed really well, and if we can just get rid of over constraint, what we realize that the forces coming on each and every member is only axial, and with the minimum material we can have a very rigid structures. So, that's something we will study in this course, and we will keep discussing. We will stop here today, and we will continue in the next lecture. Thank you.